This meeting is being recorded.
So we left off with the first video from section 4.2 with our nomenclature of linear compounds. So let's take a look at how we can apply those rules to cyclic structures, specifically cycloalkanes. And the second half of this video will look at bicyclic compounds, where we combine two rings. So the same rules will apply for cycloalkanes. So that means that we pick our parent based on the longest ring, or sorry, the largest number of carbons in a ring versus the largest carbon chain. And then we also would like to number our substituents with the lowest numbering system possible. So let's take a look at this trimethyl cyclohexane here below. So over here on the left, we've numbered our carbons 1, 2, 3 this way. Of course, we know there would be 4, 5, 6 if we continue numbering. So that's where we get that cyclohexane parent from. And now my three substituents, I have 2 methyls on carbon 1, and then I have 1 on carbon 3. So I could call this a 1,1,3 trimethyl cyclohexane, versus if I were to number this ring this way, I would have a 1,3,3 trimethyl cyclohexane. So when we get to the second digit in our two scenarios here, we see that this side would win because it's lower overall, right? Just because it says beats doesn't mean that it's a higher number. It actually means the opposite. It beats it because it's the lower system, lowest numbering. So again, let's review our rules. So first, we're going to put a number on each of the substituents and name each of them. This will be before our parent chain in alphabetical order. We will use prefixes such as di, tri, tetra, penta if we have 5 of the same substituents, if they're identical. So if we have 2 methyl substituents, it will be dimethyl, for example. But it's good to note that when we alphabetize these things, di and tri prefixes are ignored. So if you have dibromo versus dimethyl, you would put the bromo first, right? We just ignore the di or the tri. But in rare cases that you keep, that you do have tetra and penta, you would keep those to alphabetize. But more likely, you're going to ignore the di and the tri. So again, this is our summary list. So we have ID the parent, name your substituents, assign a locant in step 3, and then put everything in front of our parent at the end. So that's our summary of the rules. Let's look at some pulling them all together here. So we know that our parent in this case here would be the cyclic structure in the middle, right? That's our longest continuous carbon chain. None of the linear structures, like this ethyl group over here, are more than 6 carbons. So we're going to go with our parent being a cyclohexane. So we've identified the parent, and they've already have the numbering shown here for all the substituents. But if we started numbering with our carbon 1 anywhere else, we would not end up with this lowest numbering possible. So you can try different scenarios. Like you could start here, 1, 2, 3, 4, 5, 6. Right there you see that we have a 1, 4, 4, 6 substituent. So you can try different variations until you are convinced that you have the lowest numbering system overall. So in this case, we have a tert-butyl group there. We have an ethyl group here, and then we have 2 methyl groups on this carbon 4. So if we were to put this all together, then we have on the carbon 1 a tert-butyl group. On carbon 2, we have our ethyl substituent, our ethyl group, and then at carbon 4, we have 2 methyl substituents, so we can call that a 4, 4 dimethyl. So now we're going to alphabetize these. So Remember our prefixes di and tri get ignored. Notice with tert butyl, we also will ignore the tert. So butyl is what we alphabetize here. Then ethyl is our next in alphabetical order, and then methyl. So we have B, E, M as our alphabetizing rule here. So that's why these substituents are placed in that order. It just happens to follow the same order numerically, but sometimes you might see like a 4 tert butyl, 2 ethyl, and then a 1,1 dimethyl, for example. The number of the locant does not correlate at times with the alphabetization. So let's look at bicyclic compounds now. So we know how to name linear alkanes. We've looked at the rules that apply to cyclic structures, so cycloalkanes as well. What about bicyclic compounds? So now, as the name implies, we have 2 cyclic structures, so 2 rings, 2 fused rings. And we're going to learn some rules for this nomenclature as well. But mainly you're going to have to use this word bicyclo in front of the parent name. So let's take a look how we could accomplish this. And oh, I should go back. Note that this structure here is the same as this structure here. We've just rotated it or shown a different angle of view. But this group that's pointing out here is now pointing up here. So this is our second ring. So where the 2 carbons, or the 2 rings connect, those carbons are called the bridge heads. Right? So our 2 rings fuse together, those carbons are called the bridge heads. So we have to talk about the different paths, the different bridges, right, that we want to take in this compound. So when we name this, we count the total number of carbons in our structure in both rings. So looking at these 2 structures down below, we see that there are 6 carbons total. Let's see, 1, 2, 3, 4, 5, 6 in this first ring. And then there's only 1 additional carbon here, so there would be 7 total. We don't count the bridgeheads twice, so that's why the parent is given as a heptane down below. So starting at the bridgeheads, the numbering that you see below is how we would give these numbers in the middle here, the paths that we have to take. So these are both bicycloheptanes, these 2 structures, but this one on the left here, this has a 1 carbon bridge here and a 3 carbon bridge over here, and then a 1 carbon bridge up top, versus the other structure has the same 1 carbon bridge up top here, but we have 2 carbon bridges down here. So that's where these numbers come from. You start at a bridgehead, you go down the longest bridge first. So say I start here, I'll go 1, 2, 3 carbons, and then back to my bridgehead. So that's where that number 3 comes from. So we have bicyclo 3, a 1 carbon bridge here, 1, and then 1 up here. Both of these second bridges, you could go down either path and it would give you 1 and 1. So altogether, we would have a bicyclo 3.1.1 heptane. And then over here, starting at a bridgehead, I go down my longest path, my longest bridge. So I have a 2 carbon bridge there. My second longest path is another 2 carbon bridge, and then I have that 1 up top. So again, we have bicycloheptane, but the numeric, the 2 to 1 comes from those 3 bridge pathways. You always start down the longest bridge, and that will be your first number. So let's take a look at how this works with substituents. They do not give us an example in here, but say we had a substituent on this carbon here. We'll work through some practice problems then that will tell us how to get the lowest numbering possible. When we get to bicyclic compounds, sometimes it's a little more confusing how to get that lowest numbering possible. And then we'll pick up with the next section, 4.3, constitutional isomers, in our next video.